last week, oh sorry, we saw ourselves. Yes, that was last month. Last month was last week. Today, last week we talked about sampling, and today we'll be continuing with sampling. We'll be continuing with sampling and theory. We'll be continuing with sampling theory. So please, I want us to pay attention to all we're going to be talking today. We'll be talking now. Sampling theory, and it's just I can't unmute every one of us. I would have loved somebody telling us what sampling theory is all about. But in other case, let's just continue and catch fun with ourselves. Now, there are we looked at sampling theory last week and we tried to establish some facts about sampling theory. But today, let's look at two ways of collection of statistical data. Two ways of collection of statistical data. We have the complete enumeration, that's the census, and two, we have the sample survey. And what I'm saying, I think if you could remember, I made mention to it last week when we were going through our classes. Now we'll also have now let's look at the population of the universe. Now the totality of statistical data forming a subject of investigation. When we say population or the universe, we are talking about the totality of statistical data forming a subject of investigation. The totality, everything coming together, forming a subject of investigation. Now let's say for example, we want to know the number of students in JPTS. In JPTS, the number of students, that's the population, the totality of statistical data that will form our investigation. We want to know, okay, the numbers of students in JPTS, we want to use the number for a particular statistics. So all we're just talking about is telling about the population of the universe. Now we looked at another one, sample. This is a portion of which is examined, a portion of which is examined with a view to estimating characteristics of population, with a view to estimating the characteristics of population. If we could recall, last week I was making some analysis saying federal government is giving out 5,000 and we want to make sure that this thing goes around in all the states. Then we'll pick samples from different states to make sure that this thing shares around that everybody in, if not everybody, but everyone in Nigeria, every state in Nigeria, and every group or community in Nigeria gets this amount of money the federal government is going. So that is taking samples of the the population, taking samples of a particular area. Now, method of samples. Method of samples, we have simple random sampling. Simple random sampling. Now, last week we talked briefly about these areas, simple random sampling. And in simple random sampling, we talked about simple random sampling without replacement. Now, when I mean without replacement, taking a sample or taking something from, you have 12 eggs or 24 eggs, or you have a crate of eggs. Let me use that word. You pick one without replacing. That is random sampling, trying to take samples randomly without replacement. Then we have another one, random sampling with replacement. Okay, you take this sample and you refund it back. That is random sampling with replacement. The number two, we have systematic sampling, systematic sampling, and we also have uh, stratified sampling. We also talk about have stratified sampling, cluster sampling, quota sampling, purposive sampling or judgment sampling, purposive sampling or judgment sampling. Now let's quickly look at some important terms associated with sampling. What are those terms associated with sampling? One, we have the parameters. This is a characteristics of population based on all the units of population. Now, it is a characteristics of population based on all the units of population. That is when we talk about the parameters with parameter. Now, when we look at statistics, a statistical measure of sample observation, and as such, it is a function of sample observation. It is a statistical measure of samples observation, and as such, it's a function of sample observation. Statistical inferences are drawn about population values. Statistical inferences, statistical analysis are drawn out about population value. That is based on parameters on the sample or parameters based on the samples, observations, statistics. That is when we talk about the observations, this we talk about the statistics, and these are usually followed or usually following the table you see. You see my measure, you see my parameters, you see my statistics. Now under the measure you see the mean, the population proportion, the standard deviation, and you see their shortcuts here, like what we call shortcut or their representative, what you used to know them, because we're going to do some calculations here and their statistical things like that. Now, sampling distribution. Now, start taking a look of population of n unit. Let's take a look of population of n unit. We can draw many samples of fish size in n. Now, taking the population of cap n unit and let me say the total unit, and we can draw a fish size of the lower case n. Now, in the case of sampling with replacement, the total number of samples that can be drawn is n. Please note, in the case of uh, in the case of non-replacement, in the case of sampling with replacement, sorry, in the case of sampling with replacement, the total number or the total number of samples that can be drawn is n, and when sampling is not replaced is without replacement, the total number of samples that can be drawn is c subscript n, superscript n, and subscript small n. It is possible to obtain the value of a statistics t from all possible samples of a fixed sample size along the corresponding probabilities. Then we can arrange for values of statistics, treating them as random variables. In the form of probability distribution, such probability distribution is called sampling distribution. Such probability distribution is called sampling distribution. Let's quickly look at basic statistical laws, basic laws or rules guiding the statistics or statistical profession. Law of statistical regularities. Number one, the law of statistical regularities. It states that a reasonably large number of items selected at random from a large number of items will, on the average, represent the characteristics of the group. It states that a reasonably large number of items selected at random from a large group of items will on the average represent the characteristics of the group. Now, what are we saying in this? For example, we what this is telling us is, for example, we want to get get the population or get the population in a particular group. Then if we take a large number of people, let's say for example we want to like get some statistics of the Hausas, Igbos, and Yorubas in Nigeria, not only in the east or in the west or in the south, all over. So if we have good number or large number of samples selected at random, then it will give us average representation or characteristics of the groups we have, of these groups I just mentioned. Then number two, law of inertia of large numbers. Law of inertia of large numbers. It states that large groups of data show high degree of stability because there is a greater possibility that one side are compensated by the extremes on the other side. The law of inertia of large numbers states that the large groups of data show high degree of stability because there is a greater possibility that that one side are compensated by the extremes on the other side. Then the third one we'll be looking at is central limit theorem. Central limit theorem. Now, limit theorem says that if x1, x2 to x3 to x infinity or xn is a random sample of size n drawn from any population um, having a mean and a variance, then the distribution sample mean is normally distributed with mean and variance all over the sample size, all over n, the sample size, provided n is sufficiently large, that is n is tending to infinity, where mu um, standard deviations respectively are population mean and variance. Population mean and variance. Now, the mean of the statistics is called expectation. Please let us take note. The mean of the statistics is called expectation. The mean of the statistics is called expectation. And standard deviation of statistics is called standard error. Please let's note this. We'll be doing some calculations, and I want to advise us on this ground. Please let's go and practice how to use the distribution tables. Let's go and practice them. If maybe I'm or able to share my screen, I think I would have tried to do it. But on your own, just try and practice them, because we'll be solving some questions using them from our next classes. So we might not be talking. Let's get real into statistics. So we're going to be doing some examples, and we'll give some classwork you have to submit. Even if you can't share the screen, as soon as you finish, send it to my email. That time, within the time limit we're going to be in class, that will start from upper class. So please, let's get prepared. And it's very, very important that we all do the assignment. I'm not going to be giving out home take assignments from next week. I'm going to be taking reclass assignment. I think that is what I'll use as my continuous assessment to make me know that you guys are actually following me. Now, the standard error, remember, recall that I said the standard deviation of statistics is called standard error. So let's not be confused about that. And it's denoted by SE. The standard error of common statistics. Now, let's see some formula, the statistics and the standard error. Single mean, then we have the variance all over root n. Now, n is the number of sample. Then the difference of mean x minus y is the root of variance squared all over n plus variance squared all over n squared. Then the single proportion p is the root of p multiplied by q, or pq all over n. Then for the differences of proportion, p prime minus p prime prime then gives us the root of pq into 1 all over n prime plus 1 all over n prime prime. So the factor n um minus n all over n minus 1 is known as finite population correlation factor, FPC. So this is, you can see that on the slide, is on the table. Thanks to the man on the studio that is following me. Mr. Yomo, I greatly appreciate that. Now, this is ignored for large proportion. This formula I just quoted is ignored for large proportion. It is used when the sample all over n is greater than 0.05. It's greater than 0.05. Okay, now let's take as the classwork. This is an assignment for you. Let me not give you as a classwork. And I've already stated the answers. Number one, let's take it down. A simple random sample of 36 is drawn from finite population consisting of 101 units. If the population standard deviation is 12.6, find the standard error of sample mean when the sample is drawn with replacement, A with replacement, B without replacement. I repeat it again. A simple random sample of size 36 is drawn from finite population consisting of 101 units. If the population standard deviation is 12.6, find the standard error of sample mean when the sample is drawn A with replacement and B without replacement. So if you're on the screen, you can see the answer there to make sure you work guidelines. Now, one thing I want to tell you when working about on this, first of all, state the given parameters. State the given parameters when working on this. So from there, you can work. Don't say because the parameters are already in the question, you just start imputing the formula. No, before the formula, state the given parameters. Then you bring up the formula and start imputing to get your answer. Question number 2. A random of 500 oranges was taken from a large consignment and 65 were found to be defective. Show that the standard error of the proportion of bad ones is a sample of the size of show that the proportion of bad ones in a sample of this size is 0.015. A random sample of 500 oranges was taken from a large consignment and 65 were found to be defective. Show that the standard error of the proportion of bad ones in a sample of this size is 0.015. Is 0.015. So please, let's try and attempt it. Let's try and attempt it. Now let's look at point estimation, theory of estimation, theory of estimation, theory of estimation. Let's look at point estimation, point estimation. Now, point estimation is when a single sample value is used to estimate parameter. Point estimation is when a single sample value is used to estimate parameter. So that is when we talk about point estimation. Then the other one is interval estimation. Interval estimation. Now, this is used instead of estimating parameters by a single value, an interval of value is defined. It specifies two values that contains unknown parameters. Now, interval estimation talks about two values or specifies two values that contains unknown parameters. You don't know the parameters are not given, they are not there. So this is where you use interval estimation. You can see the formula where I try to do P into T, that is T into T, that is the sample value, is less than or equal to theta, that is the parameter, or less than or equal to T also, T prime prime. Now this will give us 1 minus A. Then T prime prime is known as confidence interval. So T prime prime is known as confidence interval. A is A is called level of significance. Now, for example, 5% or 1% significance. Then 1 minus A is called confidence level. That's 95 or 99. Then confidence, let's talk about confidence level now. Confidence level. Let's talk about confidence level. Now, this is the level in the probability value associated with confidence interval. It is a confidence level. It is a level in the probability value associated with confidence interval. It is often expressed as a percentage. For example, say the confidence level is equal to 1 minus 0.05, which is equal to 0.95, which is a 95% confidence level. So we're going to be seeing some questions like that, and we're going to be trying to establish the fact or solve them. Determination of sample size by mean. Let's look at the determination of sample size by mean. Now, if you can see my screen, say here the following factors must be known. The desired confidence level must be known. 2, the permissible sampling error, that is E is equal to mean minus mu. So then 3, the standard deviation, the standard deviation. Now the size of sample mean is given by, please, n, which is the sample number, the number of sample, then variance z all over e all squared. So that is the size of sample mean in the size of sample mean. I said the size of sample mean is given by n. That is n is used to small lowercase m or lower capital M or small n is used to denote the sample mean. So I said n is equal to variance z all over e all squared. Then the following factor, also we should note the following factor. Now, the desired confidence levels, the permissible sample error, which is E, is equal to P, capital P minus lowercase p, the estimated true proportion of success. The size of sample mean here is given by n is equal to bracket open z prime p q all over e squared, where q is equals 1 minus p, where q is equals 1 minus p. Please try to note we are trying to establish a fact here. So now if you see, if we go to my slide 13, we see a standard deviation and confidence interval table or chart on there, and we'll try to understand that also. If T is statistics, then 95% confidence interval is given by T plus or minus 1.96 standard error of T. Now, and if it is 99% confidence interval is given by T plus or minus 2.58 standard error of T. Now, these are established facts which we can get from our table. We can get it from the distribution table. So I encourage everyone, please let's try and download the distribution tables. Now, even get the chi-square or chi-square, the ANOVA, F distribution table. So we have lots of them. I think we might be working with 2 or 3 tables. Let's try and get the tables. Now, I want us to notice that there are 5 ingredients to any statistical test. There are 5 ingredients to any statistical test. Number one is null hypotenuse, is denoted by HO. Null hypothesis, sorry, null hypothesis. Number two, alternate hypothesis, alternate hypothesis. Number three, test statistics, test statistic, test statistic. Number four, rejection or critical regression region, rejection slash critical region or acceptance of hypothesis, acceptance of no hypothesis. Then number five, conclusion. Number five, conclusion. These are the 5 ingredients of any statistical test. Now you have to test for the null hypothesis, the alternative hypothesis, the test statistics, rejection, if you are rejecting it or accepting the hypothesis, and the conclusion. So, and please let's take note, we might be given a project whereby we'll have to use all this too. Now, in the null hypothesis, there is no significant difference between two values. When we say null hypothesis, we mean there is no significant difference between two values, statistics and parameters, or two sample values. Now, let's take for example, um, 1 plus 3, 4. Then 2 plus 2, 4. So is there any difference between the answers, the values we got? Now there is the same thing. So that is exactly what we're talking about, the null hypothesis. There's no significant difference between them, between the answers you got from either 2 plus 1 or, sorry, 3 plus 1 or 2 plus 2. Then the alternative hypothesis denoted by H1, that is denoted by H1, then if the above difference is significant, is when the differences are significant, when there are significance between them, the statement to be accepted if the null is rejected. So if the H1, the alternative hypothesis of or the above statement is the difference is significant, when their differences are significant. Now, don't forget that the non-hypotenuse is okay, there is no significant differences between them. Now, let's take for example, let's take this also. Um, uh, uh, 3 plus 2, 5, right? 3 plus 2, 5. Then 3 multiplied by 2, 6. Now, what will you want to tell me? You see that we have differences between them. Yes, there might be 3, 2 involved and giving us two values. Why? Because we have the multiplier or the addition sign changing the values which we got or which we intend to get, making it try bringing about differences between their answers. Then type 1 error. Type 1 error. In a hypothesis test, a type 1 error occurs when the null hypothesis is rejected, when in fact it is true. Now, this occurs when the null hypothesis is rejected and the fact is true. That is, HO is wrongly rejected. Now, let's say for example, let's make an example. Now, every one of you are applying for a JPTS program, and we JPTS is doing screening. You have, and the criteria is you must have your 5 O level credit, and JPTS just doing screen everybody and screening people that has less than 5 credit out. And you, someone has you have 5, in short, you have 7 A's, and at the end they screen you out that, oh, this person is not qualified. Now that is an error. That is an error because you are actually qualified. Now the truth is you met the requirement, so why would they screen you out? So it's an error. The same thing happens sometimes when we working on statistics. So that is what we call type 1 or type I error. Type I error. So it is, I said, it occurs when the null hypothesis is rejected. There is, you just say, okay, there is no significance between them, you reject it, when in fact there is actual significance between them. So it is wrongly, this is where, when we talk of type 1 error or type I error, it is when the hypothesis is wrongly rejected, just like the examples I made. Now, p type 1 error is equal to significance level, which is equal to 1 minus a. Type 1 error is equal to reject hypotenuse all over, reject non-hypotenuse all over non-hypotenuse is true. So rejecting it when it will know it is true. So that is type I error. Now, type I error, II error, type 2 error. Let me use that word, type 2 error. In hypothesis that a type 2 error occurs when the null hypothesis is not rejected. When the null hypothesis is not rejected and when in fact it is false. Now you see this. Now let me go back to the instances I made about JPTS screening. You come in, everybody come in, and someone that has only one credit is accepted when he or she is was supposed to be rejected. So that is type 2 error. That is type 2 error or type II error. So it's supposed to be rejected and they are accepting him. Sometimes some people will say, he has leg or she has leg. No, it's not that the person has leg. That is an error from the person screening or whoever that is imputing the data. Then type 2 error, this is when accepted hypotenuse all over hypotenuse is not true. Accepting a condition when the condition is not true. Accepting a condition when the condition is not true. Um that is there. Then the next one we're looking at here, we have the decision. Now let's look at this table, slide 18. We have the decision reject non-hypotenuse, accept non-hypotenuse. Now the decision you have to make. Now for the truth, if non-hypotenuse type 1 error, then you accept is a right decision. If okay, there are no significant differences between them, then you accept it is a right decision. Now for H1, then the right decision is type 2 error. If there are differences between them, is type 2 error. So we were able to establish that fact. You can see some little explanation on my screen where I said P reject non-hypotenuse all over non-hypotenuse is true is equals type 1 error, which gives us level of significance So these are gives us risk. And also said non-hypotenuse, accept non-hypotenuse all over. Non-hypotenuse is not true. This is type 2 error. This is consumer risk. The first one is producer's risk. Producer's risk. They are accepting they are accepting what is not true, or sorry, they are rejecting what is true. They are rejecting what is true. And the second one, then the type II error, is consumers risk, because they are accepting what is not true. A type IR error is often considered to be more serious and therefore more important to avoid than a type 2 error. Now, let me ask, why do you think this is real? This is true, that a type 1 error or a type I error is often considered to be more serious and therefore more important to avoid. Why? Can somebody just, wherever you are seated, just think and worry about this? But let me just try to give, for example, the reason is this. If you could remember what I said earlier, a type I error is producer's error, and a type 2 error is a consumer error. Now, somebody producing especially food or beverages, and an error is there, I think, or maybe mistakenly, without knowing, added some chemical that were not supposed to be added. That is an error. Or he felt it has been added, and what was not supposed, or what should be added, he didn't add it. And this is very, very dangerous, because when humans are going to take this, and what according to your production, if you don't follow these things properly, well, your product might be harmful to the consumer. So that is why it is very, very more serious on the producer's side. So in other ways, JPTS, for example, let's go JPTS. If we don't do our best in JPTS, now it's an a type 1 error. Meanwhile, lectures are supposed to hold, we don't come for lectures, and at the end we give the students 100, they all pass, we push them. Now they will not be you students will not be able to defend the certificate outside this place. You will not be able to defend the certificate. So that is, it will be a big error on our part for not doing, meaning we are producing half-baked graduates, so which is not proper. So that is why JPTS has to make these lectures very mandatory and monitor to make sure that every lecturer is always in class as at when needed, except for technical issues which the management will consider. Now we have one tail test. Let's look at some types of tests. One tail test. Now here the alternate hypothesis is one-sided, and we test whether the statistics falls in the critical region or only on one side of the distribution. In one tail test, the alternate hypothesis is one-sided. Now, since it's one-sided, we carry out the test, test statistics we carry out tests to find whether the test statistics fall on the critical region or only on one side of the distribution. So you can see that on slide 19 on the slide. Now we also have another one, the two-tailed test. The two-tailed test. Now the two-tailed test is where the alternate hypothesis is formulated to test for differences in their direction. Here in the two-tailed test, the alternate hypothesis is formulated to test for differences in either direction. Now, if you look at my slide 19 for the first diagram, or you see there, or chart you see there, you see one side is shaded for the first one, and the other one is shaded. Now I'm telling you that what is saying that, oh, the alternate hypothesis is one-sided. Is one-sided. While for the two-tailed test, both sides are shaded. So for the differences. Now the common test statistics. Let's look at some formulas for common test for we'll be using as time permits us in this course. Now I'll state the names and their formulas. Please, studio man, just go to slide 20 for me, please. Slide 20, if you can help me. Now we have one sample which called Z test. Now Z is equal to, the formula is equal to S bar all over, okay, slide 20, slide 20, please. Now S bar minus mu 0 all over variance root n, root n, and I said n is the number of samples. So thank you very much. God bless you. Now, if you get these formulas from the from the screen, these are for the first one there is for Z test, to test for Z table using on Z table. Then number two there is two sample Z test, two sample Z test. You can see it clearly on two sample Z test. And number three, we see one proportion Z test, one proportion Z test. So we could see the formula stated there. So I want you to get used to this formula. So when, if we have time and we're using them, it might not be confusing. And on your own, try to look for problems that you could use these formulas, so and be familiarize yourself with it. So even if we don't have the time to do it, you know yourself is you already know it. No knowledge is lost. Then number four, we have the two proportion Z test. The two proportion Z test. Now let's talk about the critical value. Critical values for hypothesis test is a threshold to which the value of um, the test statistics is in a sample is compared to determine whether or not the null hypothesis is rejected. Now, when we talk about the critical value, the critical values is a test the critical value is for hypothesis test is a threshold, a threshold to which the value of the test statistics is a simple in a simple and in a sample is compared to determine whether or not the hypothesis is rejected. Now, this is a test to show whether the hypothesis is accepted or rejected. This is a test to show that if it is accepted or rejected. That is the critical value, the critical value, the critical value, the critical values. So when you hear the word critical values, know that we're talking about a threshold. A threshold is a threshold where uh, a threshold which to which the samples of the test statistics in a sample is compared, to which the test that is compared, so that to determine whether it should be accepted or rejected. It should be accepted or rejected. So that is the threshold. Accepted or rejected is the most the bottommost part. It's to know that, oh, after carrying series of tests, to know, is this should this be accepted or should it be rejected. We don't just reject, but we have to carry out more and more tests to give us a basis that yes, we are fully confident that we are rejecting this hypothesis. Critical value Z, I told you about Z table, then level of significance. For two tests, we have 2.58, and for five, that's for 1%, and for 5% we have 1.96, and for two tests then we have 2.33, and that's for the 1%, and for 5% we have 1.6. So don't cram this one. Is you can get it from the Z table. You can get it from the Z table. Is all there for us. Now let's look at, oh shit. Let's look at decision. Now decision, please. Our time is almost up. Please, I want to beg you. The assignment, take note of it. Now let's quickly talk about the decision. If a model of the computed value of Z is less than table value of Z, then accept null hypothesis. So do we get it? If the calculation we got from the Z table that the Z is less than the Z we got, the Z calculated or computed, sorry, the computed value of Z we calculated is less than the table value of Z, then we accept the hypothesis. We accept the null hypothesis. That is, calculated Z is less than table Z, then we accept. Then if modulus of computed values of Z is greater than table value of Z, then we reject the hypothesis. We reject the hypothesis. We reject the hypothesis. Now, as a matter of time, before I round up, let me just quickly run down the steps in hypothesis testing. Number one, identify the null hypothesis and the alternate hypothesis. Two, choose 1 minus a level of choose level of significance. That's 1 minus a proportion. The value should be small, usually less than 10%. It is important to consider the consequences of both types of errors. 3. Select the test statistics and determine its value from the sample data. Then 4. Compare the observed value of the statistics to the critical value obtained for the choosing degree of frequency. And 5, make decision if to be accepted or not to be accepted. So these are the thing. Now I told you like earlier on, we're going to be using chi-square and ANOVA. So please go read up on them. Go read up on them. So I think I want to say it again. The time is up, and I know you guys have other classes. I want to say thank you for listening to me. I think we'll continue from here next week. And please, I want to beg every one of us, let's try and get our chi-square tables, ANOVA tables, F distribution tables, Z tables, so that when we do some examples next week, we'll be able to follow and you can solve and turn in your answers to
Simon.
me. Thank you very much, and God bless you for listening to me. See you next week.